Just the introduction. This will be all about how the engine works, all the different parts, the different pieces. So to get started, let me just set the tone here. Okay. Yes, we're going to learn about Toyotas, but the ASE has a lot of stuff about domestic engines too. As you can see right here, America. So that's why I got a whole bunch of domestic stuff out here. And then let me just show you guys something. Okay, let's look at. Want to look at the categories for the engine repair, and I just pulled it off screen, so just 1 second here. It's going to be. A little slow. Come on, baby. Here we go. All right, so this is what you can anticipate. So for engines, you're looking at about 15 questions that are just general engine diagnosis. Some of what that might look like is an engine has a noise. An engine has some symptom like overheating or oil consumption. You know, just types of things that engines would have that are about the whole engine, not one specific system. And then B, you got cylinder head and valve train diagnosis and repair. And what I want to pre-warn you about with that, it's not just knowing how it works. Some of the questions are going to be more about machining it. Okay, so we don't go fully into machining, but we're going to at least talk about it. So like a lot of measurement, a lot of telling if it's good or bad, and then also, at least on a surface level, how to machine it. So like a valve, for example, you can resurface a valve. You can resurface a valve seat. You can measure a valve guide. It's not just like what is overhead cam and what is dual overhead cam and what is a cam and block. So there's quite a bit of information there. And then C, similar to B, it's about the block, but not just like here is a V8. It's like here's a V8 and here's some measurements what needs to be done. I don't know. So we're going to talk about measuring the cylinders in a whole bunch of different dimensions and what those different measurements indicate, and then what would you do about it? So if you needed to bore an engine over, how would you go about it? How much would you take off, right? So like with the rotor, we've all done that. You cut enough material off the rotor to fix the defect. Well, that's not really true for engine stuff. Engine stuff, you actually have to take a specific amount off to get ready for the next size, or for the size bearing, or for the size piston. So there's quite a bit of machining discussion right there. And so these right here tend to be where the dealership techs are a little weak. Because in the dealer, you know what we do? Oh, the engine has an issue. You go to parts and you say, I need an engine. And the engine shows up. And you put it in. Well, you might do some assembly, but you're not generally going to do even really engine rebuilding. I'm just going to let you know. You're not really going to do it. The engines that I've rebuilt were in school, and then later on my own because I wanted to, and none of them were for a customer in the dealership, ever. Mm-hmm.
I always see, or very often in our dealership, the engines are either rebuilt or torn down.
Yeah. They tear them down. Like, let's say that you're Toyota and you find out that there's a brand new Tundra engine that just locked up. Mm-hmm. You're going to be like, okay, tear that down, take pictures, we're going to send to FTS. You will tear them down. But to do a rebuild, that's talking about like tearing it down, measuring everything, sending it through the cleaner, going through the machining process, remeasuring, you know, like race team style. You're just not really going to see that. You know what I'm saying? You might pull an engine out, and if it has a problem with the crankshaft, you may get a short block, and you may take the heads off the old one, put the heads on the new short block. Yes, that's not really rebuild though. That's all really part of like engine repair, and I'm more comfortable with that. That's normal to me. All the years in the dealership, that's what we did. And then later it was like, hey, I want to rebuild my own engine. That's going to be really cool. And it took me forever back here. All sorts of, just honing it, redoing all the bearings, and I realized that's why we don't do it in the dealer. There's a lot of mistakes to be made, and there's a lot of time. And remember, your dealer's a business. They're chasing the buck. They're chasing the dollar. So if they have you back there working on that engine for days on days on days, you could be probably billing more hours punching out 2 short blocks than 1 rebuild. Make sense? Then the other thing is liability too. So if you do a rebuild and something gets messed up, you rebuilt it, it's your fault. If you buy an engine from Toyota and then you put it in and it has an issue, it's Toyota's fault, so Toyota would actually pay the claim. It's not really likely that would happen, by the way, but just saying. So some of what we're going to talk about here is going to be very much for a hypothetical understanding, more so than what you're going to apply at work, and I know that. Okay, it's going to be similar in transmissions, by the way. And then D, cooling and lubrication. So oil pressure, noises could be up here in A, but noises could also be related to lubrication systems. So there's a little bit of a gray area there. And then like for example, oil pressure that's low could be like 10 different things. And so that's where we're going to really study this, how the oil flows. What happens if you find, let's say this bearing right here is totally worn out and all the other bearings are good? You know, that's no longer just a bottom end. That's no longer like a engine block diagnosis. That's more like, why did that bearing go bad? So now you got to understand the lubrication system. There's a passage that goes to that bearing. Maybe it's clogged or blocked, you know. So, and then cooling systems, I think you guys will find really easy because you've done stuff with air conditioning. So when we talk about air conditioning, we talk about the cooling system, but we're talking about it from the perspective of heating the passenger compartment. You like that? Although not right now. But another couple months, you'll like it. Well, this is more going to be from the perspective of how the cooling system cools the engine. So overheating concerns, coolant leaks, especially coolant consumption, these types of issues, right? And then last but not least, and this one is kind of a pain, to be honest with you, fuel, electrical, ignition, and exhaust systems. So that's like a whole lot of systems for 7 questions. Like for 7 questions, you're gonna have 1, 2, 3, 4 systems. So really, you might have 1 or 2 questions on fuel, 1 or 2 on electrical, 1 or 2 on ignition, and 1 or 2 on exhaust. So we don't spend a ton of time on fuel systems, but it's on the ASE. We got to at least cover some of it, so we're going to cover it at like a basic level. Why do you guys think that we don't go crazy on fuel systems in this class? It's an A1 class.
We're gonna take it next semester.
A8, yeah, exactly. So that's one thing that's a little bit annoying. It's sort of like, it's a little bit here, but it's a lot of it on A8. It's like, it's all over A8. And same with electrical, could be, believe it or not, that can actually have a lot of overlap with A6. It can be a cold cranking amp test, or like a no crank concern. Some battery questions, believe it or not. And then ignition is very heavy on A8, but for us, we got to at least talk about it. It's part of the reason I drug a lot of this old stuff out. So today we're going to hit a lot of the basics. We're going to talk about distributors, and then we're going to talk about distributors one more time, just a little bit, and then that's it. We're not really going to do a whole lot of distributor work. A lot of people would laugh and be like, why are you covering distributors? They haven't been on cars since, well, Acura hung on to that for a little while, like 2001 or so. But that's still a long time ago. Most cars, distributors were done in the 90s. However, there's a chance that they could have, you know, some ignition questions, and it may actually include a distributor, so we got to go over like a very broad scope of that. And then exhaust systems, well, unfortunately, that could be on A8, but it can also be on A1 at least a little bit. So we got a whole bunch of stuff here. You total those up, your real money is going to be at A, B, and C, and then a little bit less on D and E. So going for points, this is where most of your points are right here. Does that make sense? Roberto, go ahead.
How many do you need to pass?
I think I put that on here, but I actually don't remember. I think out of 50, it might be like 34.
34, yeah.
Yeah, I think 34. Yeah. So I think you guys will be in pretty good shape if you're pretty engaged. You know, this is a tried and true class. We've had pretty good success over the years, so you should be pretty solid. All right, so jumping into it, engines. They're pretty exciting, I think. You can read these okay? So internal or external. We're going to talk about external just like for a little bit, just so you can get a cool perspective on it. There will be absolutely nothing at all in any way on the ASE about external combustion. That's like old school stuff, like really old, like American Revolution type of old stuff. Okay, and then the difference, internal combustion takes place inside the engine. So the fire is inside. And external, fuel's ignited outside, and so that's kind of what I'm saying, like generally if it's fire, and it could be something different actually, but if it's some sort of burning, it's outside. So internal or external. You guys have all heard of the ASE, right? Internal combustion engine, the ASE, ICE. So why they have to specify it's internal? Well, because they weren't all internal at one point, but now pretty much everything's internal. So you just say engine, everybody would know, like, yeah, that's got pistons and stuff. But as for what's in the engine, they do there's a lot of physics and science and math and stuff that happens for that internal combustion engine. They're using thermodynamics, chemistry, geometry, physics, and metallurgy. And we'll touch a little bit on each of those. So, like, here's an age-old question. Cast or forged? Which one's better? Forged, we're like, why? You know, so there is a lot of metallurgy type of stuff. And then if you wanted to get even, there's more than cast or forged, by the way. We just say cast or forged because that's the most common that we discuss. And so we'll talk a little bit about some of those, but here are your engines. So if you look at this, these are talking about like thermodynamics, how we move heat. If you look at, this is basically your engine. If you were to look at this wheel could do work, right? Like, tell me something we could do with a spinning wheel.
Generate electricity.
Okay, so this could actually be turning a generator. That's true. What else? Anything else? You're wearing clothes. Like, what if we used that wheel to spin a belt, and that belt did something with a needle, and it threaded the needle? You know, so you can do all sorts of weird stuff with this. But the point is, this has like, this whole thing is an engine, and it has a bunch of different things. It has a double acting piston. But basically what we're doing is we're using water in this boiler, and we're going to heat the water, and then the steam is going to come over here, and it's going to actually move that piston. When it moves that piston, it's going to move the linkage, and ultimately it's going to move the wheel. Maybe we want to have it attached to like a little paddle and have it scoop water and have the water run down a little irrigation trench to grow corn or something. Something like that, I don't know. Right, but the point is, where's the combustion?
Outside.
Yeah, combustion outside. The fire is outside. We have logs and wood and whatever, and we light it on fire, and it heats up the water, and the water boils, and that's actually how we make this thing spin. And then this is Stirling. It does kind of similar. There's actually a heat source. You could make it even a small Stirling engine, and you could have it be actually powered by like a candle. You could light the candle, and then the candle heating this bulb will actually heat the air enough to push the piston down, and then it'll cool and pull the piston up. And so there's some cool stuff. That's all basic engines, external combustion. Steam you could even talk about. We talked a little about steam already in that first one. And then we get more into modern internal combustion engines. So it's self-contained power plant, takes chemical energy, converts it into mechanical energy to do work. What the heck does that mean to you? Where does the power come from? Just told you. Think about it like from the most basic level. You all like engines, I've seen you. I've seen quite a few of you. Some car goes by. Now some of you react differently to different type of sounds, by the way. I hear some of you, V8 goes by, you just about break your neck. I heard some people, turbo 4-cylinder goes by, and you're like weak in the knees. Like, I've seen it. The straight sixes, I know who's got the ears for these things. But like, where does the power come from?
Combustion.
Yeah, combustion, the energy is the fuel. Chemical energy. So in fuel, in gasoline, unless some of you, got your big boots on, and in that case it's diesel. And so you got gas or you got diesel, there's a specified amount of energy in that, let's say gallon or whatever. You want to measure it by the gallon or measure it by the gallon. In that gallon of fuel, there's an amount of energy in there. The thing that we're trying to do is extract the energy from it. And that's actually what the engine does if you think about it. It's pretty amazing. You put the go-go juice in there, and the go-go juice gets used up, and it makes the car go vroom. It's pretty wild, but at the most basic level, that's what the engine does. Period. Now, you can go way more advanced, like how do you make more power? Well, you supercharge it, and you port the heads, and you put bigger valves, and you put nitrous, and you do all this stuff. But this is the thing, at the most basic level, all that stuff that we're talking about, all it does is allow you to add more fuel. And remember, the energy's from the fuel. So you want to make horsepers, you need to put more gas in there. You put more gas in there, you make more horsepers. But you can't just throw gas at it though. It's got to be in the right ratio. So if you want to be able to put more gas in it, you need to pull more air. If you pull more air, you can pull more gas because they have to be in a ratio, like an air-fuel ratio. Cool, so we're trying to make the engine breathe more better so we can add more gas, we can get more power, and bad emissions, and then you go to the smog graph, you get cars getting repoed, all that type of stuff. So that's basically what it does. Now let's take a look at this. Here, this is, for example, this is like your basic, we could say a weed whacker or something. This is your most basic engine. We got a crankshaft, we got a connecting rod, we got a piston. We have some mechanism where we're going to have air to come in. This one actually happens to be 2-stroke, so this one's the most simple because it doesn't need a camshaft, it doesn't need valves, it doesn't really need any of that. You could have a 2-stroke engine, tiny, well, I mean a weed whacker or a leaf blower. It's like this big, and that includes the muffler and all that type of stuff. It's pretty wild. Think about it. So essentially, it's what we're going to do. We're going to get air and fuel into that sucker. We're going to compress it, because when we compress it, we heat it, and that makes it more like ready to burn. It's actually kind of hard to burn if you don't compress it. With a spark plug, you definitely won't get it to burn. If you don't compress that air and fuel, at least, close to 100 psi, you ain't going to catch it on fire. That's not to say you couldn't maybe catch something on fire if you had a big old blowtorch and that type of stuff. But to actually use a spark plug, we're going to bring it up, compress air and fuel, light the spark plug. That's going to begin that word we called combustion. So all combustion means is we're burning it. So, but burning it is like, it doesn't really make you think about it the right way. The way we want you to think about it, we're combusting it, which means we're basically performing an action that's going to extract the energy from it, right? It had potential energy in the gas. We want to take the energy out. We want to take that chemical energy, we want to convert it to mechanical energy. Pump the pistons, turn the crankshaft, turn the transmission, spin the drive shaft, spin the rear tires, and get yourself a ticket. That's called an unsafe start, by the way, in case you haven't ever seen one. You burn out, you get an unsafe start. What was unsafe about it? Well, that could be debated. So that's what we're trying to do. We're combusting it. Kind of make sense? You could take wood and you could combust it. But like generally, if you're trying to do work with it, it makes more sense to think of it as combustion rather than just burn it. Burn it makes you think it's just like gone. It's not gone. We've extracted the energy. All right, cool. Now, here's kind of what we were saying. And you people will appreciate this if you like that Dorito thing that goes around, whatever. These are all engines. So a 2-stroke air-cooled engine, very basic. You could get a little bit more complex and you could go to a rotary. A rotary it's kind of weird. There's no valves, there's no cam. I mean, they're small, they're compact. And so if you look, we have an intake, a compression. Where the ignition occurs is not a stroke. We have the actual power stroke, we have the exhaust stroke, but we have it happening in multiple chambers. And so to say an internal combustion engine definitely has pistons is not real accurate. It could actually be this rotary right here. The combustion is occurring where? It's inside. So, cool. Now, let me ask you this. Here's a question for you. What initiated this combustion? What started that combustion, by the way? The actual flame. What started the
spark
fire?
plug.
The spark plug, exactly. So this would be, more specifically, a spark ignition internal combustion engine. Make sense? You know diesel don't do that. This is the number one thing everybody knows about a diesel. It don't have spark plugs. Like, yeah, that's true. And then somebody said, but it has glow plugs. And it's like, yeah, but that's not really important though. Because there's lots of diesels that don't have glow plugs. And there's a whole bunch of clapped out diesels that the glow plugs don't work. So a compression ignition engine is where they make so much compression, the compression alone will start the combustion. Kind of make sense? So for us, our focus is going to be on spark igniting. Make sense? Because that's what we do. Now, here's a little bit more of a common one for you. You can see it's the spark ignition, could be compression. Spark, for example, the spark occurs, combustion begins, combustion continues, which is pushing the piston down. Pushing the piston down is caused by, if you think about it, the combustion started, and then that flame is consuming the gas in the air, and it's expanding. So if it's expanding, where's that expanding gas trying to go? It's increasing the pressure, right? So that pressure is trying to blow out the valves, it's trying to blow out the head gasket and all that stuff, but that stuff should be strong, so what's it going to do as a result? Push the piston down, exactly. So that power stroke right there, the combustion stroke, you may call it, that's actually all we're really trying to do. It would be great if every stroke was the combustion stroke, but unfortunately, that's what we're after, but unfortunately, we have to do the intake stroke, the compression stroke, then we get the fruit, and then we got to do the exhaust stroke to clear it out. So you got to do 3 strokes that are just necessary to really achieve the one. So like, you zoom out, and this is for any of the motorcycle people will be like, oh, what's better, 4-stroke or 2-stroke? You know, like, there's sayings. You can put them on bumper sticker. If you ain't mixing gas, you ain't hauling your butt around and things. Like, effectively though, if you think about it, a 4-stroke has intake, compression, power, good, exhaust. A 2-stroke, it's kind of weird, and there is a slide on here. A 2-stroke basically has power and intake on one, and then exhaust and compression on one. It gets a power stroke every 2 strokes. So it's basically like power, not power, power, not power, power. A 4-stroke is sort of like not power, not power, power, not power, not power, not power, power. A 2-stroke will have a combustion stroke 2 times for when a 4-stroke would only have 1 time. Make sense? So back in the day, 2-strokes made a lot more power because they had a lot more combustion strokes for revolution, right? Per revolution of the engine. 4-stroke, think about this. To complete the 4 strokes, how many times do you have to turn the crankshaft? Intake turns it a half. Compression turns it a half. Power turns it a half. And then exhaust turns a half. 2 times, which is called 720 degrees. So if I say 720 degree cycle, y'all know what I'm talking about now. 720 degree cycle is intake, compression, power, exhaust. The crankshaft went 2 times. 2 times. If you know like snowboarding, you hit the jump, you spin around once, what'd you just do?
360.
That was a 360, but see, a 360 ain't good enough. You got to do it 2 times. That's a 720. Man, he went off the jump and busted a 720. It was 2 times. Cool? We don't call it double 360. We call it 720. All right, so that's kind of what we're after here. And you can see there are the 4 strokes. Now this one is a little bit different because I don't see a spark plug here. There is no spark plug. This is a diesel. So here we've got, diesels are still 4-stroke, by the way. You may call it 4-stroke or 4-cycle. So if you hear 4-cycle, it's 4-stroke. Cycle strokes, Same. Intake, then look right here. This is compression, but it also says what? Injection and ignition. That's kind of weird. And this is why. If you backed up to a gas like this one, this has the carburetor. Roberto, take a peek at this. This one, because it has a carburetor, air comes in and fuel mixes with it. And then what gets sucked in on the intake stroke on this carbureted engine? Air and fuel. Cool? So in the intake stroke, there's already fuel. Then we compress air and fuel. But it doesn't light until we ignite the spark plug, and then that ignites, right? Diesel's way different. The diesel pulls in just air. There's no fuel in there because diesels don't have carburetors. They can't have carburetors. A diesel with a carburetor wouldn't work. Diesels have to have fuel injection, but not only that. You remember how GDI is a thing, right? Direct injection gasoline engines. Diesel's been like that for like forever. In a diesel, on compression, when it gets to the top, we're gonna time at what exact precise point we spray the diesel. So we have air compressed, and then at the right moment, we spray the diesel, and that's already so hot that that's gonna start the combustion, right? So like a diesel is gonna have really high compression, like 20 to 1, something really strong. Cool, but how did we start the combustion cycle in a diesel? Tell me back. What initiated the combustion?
Compression.
True, but at what precise moment did it start to burn? How do we control that?
When you inject it.
Exactly. We control timing of a diesel by the fuel. So the diesels are funny. Like basically fuel calls the shot. The fuel's in control of everything. On a gasoline engine, you hit the throttle, you hit the gas pedal, the go pedal on the right side, the skinny pedal. That makes air come in, right? You on a diesel, it doesn't even have a throttle. It's just sucking. Whatever air it can get, it's just like, give me whatever I can take. I'll take it all. But what controls the RPM is how much fuel we spray. What controls exactly when the combustion starts is when we spray the fuel. Fuel being the diesel. Make sense? The problem is, on a diesel, we have such high compression that actually it wouldn't even be able to hold up to that 20 to 1 compression. Gasoline can't really handle those types of compression numbers. It's going to be out of control. Diesel's hard to ignite. It needs really high compression, but it's kind of stable in that way. Right? So we start the combustion with spraying the fuel, boom, and that's actually going to push it down. And then, we still have to exhaust it. And then we start the intake again. So there's your 4 strokes on a diesel. Realistically, that's probably about all you'll ever need to know about a diesel, unless you change industries, which I'm not telling you to do. Unless Toyota says one day, like, hey, we're going to put a diesel in our trucks, but I don't think that day's coming because the glory days for that are gone already. Diesels are powerful. Diesels run really good. Like, if you were to offer somebody, hey, that Tundra, let me give you a diesel, and then you can be passing everybody hauling your boat, leaving whatever the river, and like, they probably love it. But they've been trying to crack down on diesel emissions. Diesels used to not need a smog, now they need a smog. Diesels are being squeezed, and if Toyota didn't jump on it 15 years ago, 10 years ago when it was easy, I don't see them ever going for it. I don't think you're ever going to really work on diesel, unless you get your own. Unless you get a tractor, unless it's something that you're doing, but for your job, you don't really need anymore. Go ahead, Mitchell.
All I know is Toyota mainly does diesel in like their foreign markets.
Exactly, and I don't think you'll see it here. So that's true. If you move yourself to South America and you get a Hilux diesel, let me know. That'd be cool. Bring it back.
Like there's a product.
I'd be potentially interested. But, unless you go work on Hino or something, you're just not really going to see diesel. Cool. So if you really understood what I just said, you know more about diesels than most people. Well, I'm serious. Most people are like, yeah, diesel, they don't have spark plugs. And that's where the whole conversation ends right there. That's it. That's the whole, like, yep, you got it. Okie dokie. Okay, so continuing. So again, this is going to talk a lot about the physics, and I'm going to kind of cut it down to some bare essentials. So check this out. This is Charles' law, which actually you've heard before. I just didn't call it out as Charles' law. If you look right here, In a sealed chamber, pressure and temperature of a gas are directly related. So remember how we were kind of talking about with AC lines, you could feel the line and be like, that line's hot, so what's that mean? Exactly. So now think about that. If we take air and fuel and we light it on fire, is it going to be hot? So what's the pressure going to be?
High.
Then we push the piston down. That's it. There's your physics lesson. Have a nice day. Boom! Like that. And that's pretty much what this is really trying to explain. So if you are reviewing the book, it's going to talk a lot about the physics, but to me, I don't think it's really all that technical. It's kind of simple. Cool? And again, more and more, it even goes into some of the more details, like latent heat energy exists in different types of fuels, so that's kind of what I was saying. There's a specific BTU per gallon of gasoline. There's a specific BTU per gallon of diesel. Which one do you think has more?
Diesel.
So for the purists, diesel is the better fuel, right? I mean, technically, the diesel has more BTUs in it than the gas does, than gasoline. Oh, petrol, if you will, in your aluminum engine. So in that way, diesel does make more power. That being said, it comes with some expenses though. Like diesel has more BTUs, so that means the engine's gonna be stronger, stuff's gonna be beefier, fuel system gonna have to be more powerful because we're injecting the diesel into the high compression cylinder. So like my rebuttal, if you will, to a purist diesel person is like, diesel's better, it's got more BTUs. It does, but it costs more money to extract those BTUs. So like, where are we at now? Okay, cool. But a gas engine that breathes well, the gas is cheaper, although it shouldn't be because diesel's less refined. So you'd think that diesel would be cheaper. Diesel was cheaper when I was a kid. Diesel was way cheaper than gas. But then they're like, no, diesel is less refined and it has sulfur, so we got to take the sulfur out, we got to take this, we got to do these additives, they got to do so much to make the diesel burn clean enough that the diesel's more money and the engines are more money, and then all the drive lines got to be beefier. So it comes down to, what it comes down to? I'm going to tell you the truth. It's personal preference. Diesels are nice to drive. I don't want to work on it. That's it. Have a nice day. Oh, and coal, by the way, that also has BTUs. I know coal is a bad word, but coal's got some BTUs in there, as you can see. Gas 14,000, diesel 25,000. Coal, depends on the type, but coal still got BTUs. We could burn that too. Probably not internal combustion, though. Okay, so again, the physics, pressure, and volume, I think you got it. Now, here we go. Who is this?
Edward.
I already knew it. Okay, I'm gonna help you clarify something. People have had, this is a conversation that I've heard a million times. What's the difference between horsepower and torque? Well, first you've got to define what each of them is. I once heard a car salesman when I was a kid, and my mom was thinking about getting a new car, and she's like, oh, we'll go test drive Hondas. And we rode in the back of a Honda Civic, and the guy was like, now, this car has a lot of horsepower, and you can tell because horsepower is what gives you that feeling like you're being pushed back in the seat. I've heard everybody explain all sorts of nonsense. And then VTEC hit. It's like, Mom, this car is kind of cool. I convinced her to buy a Chevy Cavalier. It's horrible advice, but she took it from me. I was like 9. She should have known better. So here you go. What is force? Well, or what is torque? You could say. Force is effort to produce a push or pull action. So that's essentially a measurement of work. Now torque is added to it, so I'm gonna back up just a little bit. For now, let's just talk about force. If you want to measure a force, we could do it in pounds. We're mostly going to do pounds. So like if you picked up 100 pounds, you picked up 100 pounds. You generated, to pick up 100 pounds, you have to generate 100 pounds of force. Make sense? The force has to be equal to the weight of the object. Cool? It could also be in kilograms or newtons for the people on the wrong side of the pond there. So work, however, is when a force causes movement. So that's one thing I want to clarify. If you push on this wall and I made 100 pounds of force, did I do any work? No. So here's the life lesson. if you're trying really hard, but you're not getting anything done, it's not work. It's just force. It's true. So if you try really hard to push something that doesn't move, you didn't accomplish anything. Now, you might have made yourself stronger, and in that way, I could see some benefit. But did you do any work? No, you didn't do any work. I'm sorry. You only do work when, what's it say here? You only do work when it causes movement. So the movement is the work. Now, if you were to just take up 1 pound and move it, and then over here you're going to take 100 and move it, you did more work over here because it was more weight, it was more force. Okay, so that's what work is. Cool. Equal to distance moved times the force applied. How much force and how far did you move it? Make sense? If you took 100 pounds and you moved it an inch, and someone else took 100 pounds and they moved it a mile, the one who moved it a mile did more work. That makes sense. That's why we call it work. So, first. And then power. Ooh. So power is the rate or the speed at which the work is performed. So I want you to remember that. We're talking about the difference between work and power. Make sense? Kind of? So the more power that can be produced, the more work that can be performed. It's measured in foot-pounds per second or per minute or something. So right here, does it say anything about time? It talks more about work and the forces, right? But it's not about time. So if we had those same people, right, and they took 100 pounds and one moved it a foot, cool, they did some work. If another one took 100 pounds and they moved it a mile, which one did more work? The one who moved it a mile. Come on, you know that, right? Now, which one had more power? We don't know because we didn't talk about time, right? Torque has no dimension of time in it. So we're just saying, if you moved 100 pounds a mile, really good job, but it might have taken you your whole lifetime, in which case you have no horsepower. That's really sad. That's not good. But the faster you move that 100 pounds, that's the faster the rate is, right? So the rate, that would be more horsepower. So now when you think of horsepower, you're thinking about getting the car to accelerate, right? So you're talking about taking that car and moving it a distance, correct? But you want to know how fast it can do it, all right? Because, like, let's just say, I mean, if you want to move, what's the car weigh? Make a weight.
3,500 pounds.
3,500 pounds. I can move 3,500 pounds a quarter mile. I'm probably going to do it in small sections, though. I'm going to go move 100. I'm going to set it down. Then we go get 100. I'm going to set it down. So I can do that. The problem is, it took me all day. So my horsepower was pretty low. Make sense? When you think of horsepower, you want to talk about the 3,500 pound car down the track a quarter mile in 10 seconds or less, potentially, right? That's actually more a measurement of horsepower. We don't measure horsepower in seconds though, so it's got to be in these units right here. So like, you could even say foot-pound per second, foot-pound per minute, but we don't really typically call it like a kilowatt per second or something. We'll probably just call it horsepower, because that's how much work at that rate of speed a horse can do. Isn't that kind of crazy? Somebody figured it out literally using a horse. But we'll talk a little bit more about that later. Just for starters though, work is a force that causes movement. Power is a force that causes movement, but you measure the amount of time too. Okay? So now here we've got, let's just say, Edward picked up 150 pounds, 4 feet, but he did it in 2 seconds. Edward has 1 horsepower. Woo! Right there. Whereas back here, remember, we didn't really talk about that. Right here, Edward was just like, yeah, I have 600 foot-pounds. Make sense? Actually, technically, you might have done the same thing. It's just one we didn't set the stopwatch, and here we did set the stopwatch. So now we're actually measuring more like power. Cool. So again, torque, a twisting force. So like torque is, remember, that's that's a form, what was it a form of? Power? Torque is just a twisting force, which is really more force. It's just a force. Make sense? And then if you were gonna, let's say, apply that to do some measure of movement, then that becomes work. Cool? So when you measure crankshaft's foot-pounds, that's just how much force it can do. They're not even really calculating how much work it's doing, which is actually moving it. And then if you were to actually apply it to horsepower, you'd have to do horsepower, which equals engine RPM times foot-pounds divided by 5,252. I believe the way that that formula came about was they actually measured how much work a horse can do in a specified amount of time, and then they just realized it was proportional to the amount of torque as long as you added time, right? So they came up with this formula. That's how you come up with horsepower. RPM, because think about it. If you make a whole lot of torque, but you're moving really slow, does that equal a ton of horsepower? It doesn't, exactly. So like, if you're really strong, but you move really slow, you're not doing as much work. But if, let's say, you're really strong and you're really fast, you can do a lot of work. You can move a lot of that weight down the quarter-mile track. Makes sense? So it's kind of the way to think about it. Now, the way that I like to tie that in is, let's say we've got a tractor, like a tractor with a diesel engine. They make a lot of pound-feet of torque. They can do a huge twisting force. Like if you wanted to lift up a big old scoop of rocks or something, a tractor's gonna make a ton of torque. That's gonna be really good. So torque is really high, but it's slow. So if you look at a diesel, a lot of times they have really high torque, but the horsepower is kind of low. The main reason why, it doesn't have that many RPMs. Like a diesel might be 3,000 RPMs redline, and they sound like they're going really fast at 3,000 RPMs, but 3,000 RPMs is not that fast. Make sense? So the torque is high, but the horsepower is kind of low because it's only got 3,000 RPMs. Make sense? Now let's make this a discussion about a Yamaha. I pick on Yamaha because Yamaha turns some pretty high RPMs on their 600, like on an R6. Anybody have any idea what the red line is? 18,000. Have a nice day. All 18,000 RPMs of that. But the truth is, those I pick on all the sport bikes. I pick on really all the bikes. Sport bikes are pretty fast, but actually they're trash torque. They don't have good. 600 they're just gutless. I'm sorry. 600 you're. But honestly, if you're at like 2,000 RPMs and you punch it, the thing's like loading. Please hold. Please, like, let's go, you know? They don't really make a lot of torque. They just don't. Actually, rotaries don't make a lot of low-end torque either, by the way. So if it doesn't really make a whole lot of torque, but I'm telling you that those street bikes have 100 horsepower and that tractor only has 26, how the heck is that? Because it's 18,000 RPM. So even if it can't haul a big old bucket of stones, the sport bike's like, yeah, give me like 100 pounds of stones and I'll 18,000 RPMs down the track and I'll come back and get another one. It can actually do more work. It just doesn't develop as much force. So you gotta kind of understand what you got. Now those 600s, I'm not gonna say they're not fun, but if you wanna ride one of those, you gotta keep the RPMs way up. So if you're just cruising around, even if you're at 50 miles an hour, you need to be in first gear. If you're in first at 50, 60, 70 in first gear, they feel pretty good. But your RPMs are already, 12, 13,000. You've heard of the power band? I'm telling you the power band. Depending on how that engine is made, a diesel has a nice meaty, low, torquey power band. A small four-cylinder like that, sluggish. Way up here at the top RPMs, got a good power band right there. It can do more work right there. Power, we add time in, right? It's kind of weird. You can look at the torque curves of like a dyno and be like, oh, that's kind of what I would like. I could go either way, but in your mind, I want you to think about later. You want something with a lot of low-end torque, or you want something with like a lot of high-end power. I want you to think about that. That's a good assignment for you. All right, cool. So this just goes more into horsepower and torque. A lot of that type of things. So again, like an engine, for example, I can trash talk ICE a little bit. Engines are amazing. They make cool sounds. They can make cool smells. You can have memories made. Sometimes I'll come up to a car and it'll smell a certain way. It'll remind me of a memory that I have. Like, I like all that stuff. However, I'm just going to be real with you. Engines are kind of like little prima donnas. They're like, oh yeah, I'll make power, but like at 800 RPMs, I'll barely run. And at 3,000 RPMs, I'll start to feel pretty good. But then at 6,000, I'm spent. It's like, really, dude? That's it? So you basically need between 3,000 and 6,000 RPMs that we're going to be friends? Anything other than that, you're just going to suck? You're just going to embarrass me? Apply that to an electric motor. Electric motors like 0 RPMs, I'll give you everything I got as soon as I start moving. 10,000 RPMs, I'll still give you everything I got. They will make all the power and all the torque at any range. So if you look at an engine and all those sweet memories and sounds, which I appreciate, I do, we need to put a transmission on the sucker to keep it in its power band, and electric motors like transmission, don't need it, never had one before. You hit the gas, I give you full power, we'll take that thing all the way up to 100 miles an hour. No gear shift, no transmission, no nothing, everything is direct. So from that, I'm just telling you, electric motors really got the gas engine beat. I'm sorry. But it doesn't come with the memories and the smells and the vibrations and stuff like that. That's true. It's a little bit boring, you may say. So we'll continue. So again, let's say a diesel, for example. A lot of the times a diesel's made a little different. Like a diesel could be made to pretty much run like at or near its maximum speed. So it's kind of weird. If you were to jump in your car, would you hold it to red line like for the whole rest of the day? Diesels can be made where that's fine. If you jump on a tractor, a lot of times they might not have a gas pedal. They'll have a lever like this. And you just be like, okay, I'm going to be plowing a field or whatever. You just bring it all the way to red line and run it the whole 8 hours. It doesn't care. That's how they're made. They're just different. You see what I'm saying? They're made kind of different. Our engines, they're not, at least for daily drivers, we're not designing our engines to be at or near 7,000 RPMs all day, every day. You could try it. Nate, there's some people that are in your forums that I think be trying that, because I see those pictures of those crispy cars, thinking like, I don't know. I suspect operator error, but I don't really know. I'm just saying, they got some GR Corolla, and they're not made for that. Toyotas are well-built cars, but none of those cars are made to be 7,000, 8,000 RPMs all day. Now, what happened? I don't really know. I'm just saying, I don't really know. Cool, so they're just designed different, right? Now, we talked a lot about this, horsepower and torque, but again, what does a dyno measure? And it measures both. Exactly. So the dyno will actually measure the twisting force, so that's the force, the work, but it'll also do that calculation, and that'll be able to determine power. Make sense? Kind of can do both. All right, cool. So, and here's your chart. So like, let's say this right here is, this to me is this one's a little bit sad. This reminds me a little more of like a bike. You actually got a pretty healthy torque curve right here, but you notice your torque never really gets that high. And the reason for that is, if you think about this, right, we're gonna go way into detail. You got an engine, and your engine, you have to picture it as basically an air pump. The more air it can move, the more fuel you can add, the more power you can make. Cool? So let's say at kind of low RPMs, you got your piston coming down and your intake valve opens up, right? So what's it doing? Kind of like breathing in, like you, breathing in. But it's not going that fast, so it can really breathe in, like it can pretty much pack that intake stroke full, a lot of air. Cool? Then the valve closes, then it compresses it. Now that's a whole nother concern, depending on what the compression ratio is and the rings and how stuff is sealing cool. But then we're gonna light on fire, and we're gonna burn it, the more air you had on that intake stroke, the more fuel you can add, the more power you're gonna get. That's efficiency. That's gonna be pretty efficient. Then at the end of that, you need to breathe all that exhaust gas out. So we're gonna open the exhaust valve, we're gonna push it all out. But again, the exhaust valve's open for a little while, right? Because we're at 1,000 RPMs, 2,000 RPMs. We have lots of time to pull air in, we have lots of time to get air out. You tell me how that's gonna look at 6,000 RPMs. That intake valve's only open for a second, so we're gonna try to breathe as much as we can in, but the intake valve is only open for just for a millisecond. So do you think we were able to really fill the cylinder as well at the high RPMs? And that's part of the reason why, the horsepower does go up because we're getting more RPMs, but it's all about how well we can move that air, and that's a term that's actually going to be brought up called volumetric efficiency. So if you had 100% volumetric efficiency, you'd have that engine making as much power as it possibly could. But if it starts to get into higher RPMs and it can't pull the air in fast enough, look what happens. It starts to tail, it starts to drop off. You lose a lot of volumetric efficiency, even though, remember, when we talk about power, it's got to do with RPM, right? So the higher the RPMs, more helpful, right? But the higher the RPMs, the less volumetrically efficient it is, so we start actually losing power. At some point, all the engines are going to drop off. They're going to lose power. So at that point, we're like, you know what? We don't really need to go over, in this case, we really don't need to go over 4,500 RPM. We're done. We're just going to just rev limit it right there. Have a nice day. So there's so much science and physics that goes into getting that engine to breathe, getting it to be as efficient as possible, getting it to try to fill those cylinders. So when I took the class, they always told us, you'll never hit 100% volumetric efficiency because of the friction and the intake and the bends and whatever. Okay, and then the Corvette Z06 came out and it exceeded it. And I don't really know how to go on from here. I don't, every day I wake up and I'm like, they told me something and it was a lie. And then this car comes out and it exceeds 100% volumetric efficiency. I'm thinking like, what the heck is going on? Then they get into all sorts of crazy stuff. Like when you breathe the exhaust out, they'll actually start overlapping the valve so that the exhaust leaving will kind of pull the intake in a little bit, scavenging. And it's like, you can go full on like mad scientist crazy to really understand all that type of stuff. So from a hypothetical standpoint, we can't reach 100% volumetric efficiency, except Russ can, because he's the man. All right, so this talked a lot about the engine, but just from a baseline, let's define some terms that you're going to need all semester. TDC and BDC, everybody got them? That top dead center right here. High up as your piston goes, that's TDC, top dead center. So if you're working on a vehicle and it says set cylinder number 1 to TDC, you're like, what? Well, I just told you. How are you going to figure out cylinder number 1 is at top dead center? Well, how janky you want to be. You get your screwdriver out, you take the spark plug out, you drop it down there, you turn the engine over, and the screwdriver goes up, and then it goes down, and then you're like, back up a little bit, there you go, there's TDC. That's one way. A lot of times, if you're on top dead center cylinder number 1, like on this engine right here, if you're on TDC cylinder number 1, there will be a mark on this crankshaft, which, don't judge me, I'm going to get it around there. It's actually harder than it looks. There's actually a mark right here, and I just set this TDC number 1. I didn't do a screwdriver, right? So when you're a DIY, you know some tricks or whatever. When you're working on the lawnmower, I personally would use the screwdriver, by the way. I'd use like a 1/4 inch extension. It's a little more smooth. It's not real jagged. You can do that, but like in the service manual, it may say set cylinder number 1 to TDC, or it may say, line up the mark on the crankshaft to the mark on the timing cover. Only thing is, I gotta warn you, that might be TDC of cylinder number 1, yes. But is it on the compression stroke or is it at the top of the exhaust stroke? Oh, I don't know. Genuinely, I don't know. The crankshaft is at the same point at TDC compression and TDC exhaust. I'm just letting you know. So the next thing I could do, I could actually look at that and I could see are any valves open. So if the exhaust valves are open, I'm like, oh crap, I gotta do another 360. And then when all the valves are closed and that mark is lined up, I know I'm at TDC. For whatever reason, if you need to do TDC, now you know. Now when you turn it 180 degrees from there, this piston will be at BDC, bottom dead center. We don't generally do anything with bottom dead center. The reason I want to bring it up now is because we're about to talk about compression ratios and stuff. So you need to know BDC to TDC, the movement, from measuring BDC to measuring TDC, that's the stroke. So bore and stroke become cylinder displacement. How you measure stroke is that? The bottom to the top. Okay, very good. And we're going to get a little bit more into it, but at this point, who can time check me? You got 8 o'clock?
8:20.
Pause for me, Roberto. All right, so overview of the engine, as you can see in the picture, we've got the intake, the head, the exhaust, and I do them in that order because the air comes in the intake, gets pulled into the head, and then leaves the head and goes out the exhaust. Then of course we got what we'll call the block, or sometimes what we'll do is we'll call this the top end. So right here where the head gasket would be, above the head gasket's the top end, below the head gasket's the bottom end. So if you have a problem with a piston or a crankshaft or a bearing or something, that's all bottom end problems. Whereas if you have a problem with a valve, that'd be a top end problem. In this case, I'd say if you have a cam, that's a top end problem. But if you guys look at this engine right here, you got a couple head gaskets right here. So really, this is the top end here. Guess what? The cam actually lives down here, right around this spot. So like this engine, for example, this is actually the block that comes with this. This is upside down right now. So I'm going to flip it over for you, which could be a little difficult, but anything for you? Yes. Okay. Oh, there we go. It's a big girl there. How you doing? All right, so if you look, this would all be top end. So everything here is bottom end. And guess what? This hole right here, that's where the camshaft goes. So if it's a LS, if it's a old V8, if it's something like that, the cam is actually in the bottom end. So it's kind of weird. The ASE is going to have questions about engines like this, because this is still common. This is still in use right now, like today, like a Hemi or a Ford abandoned it a while ago, but like generally older domestic V8s would have this. All the GM small blocks would have this. 350, the LS, whatever, LS 1, 2, 3, 7, 9, all of them like this. Cool. So we'll talk a little bit more about this in a bit. And just overall, kind of looking at this, let's transfer that to something you're a little more familiar with. Now this one's a bit older, but if you look, this is actually Toyota. This gray part right here is the intake. I'm going to be whipping this thing all over the place here. Right here, this is your throttle body. So when you go hit the gas pedal, it's actually going to move a cable because this one's kind of old. And you can see right here, opening this throttle right here. Can you hear it now? Boop, 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 boop. That's what you're doing when you hit the pedal. This assembly is the throttle body. Okay, the throttle body's still there, but it's changed a bit. The throttle body was literally a valve. Sometimes we'll call that valve the butterfly. You ever heard it called the butterfly? It's like looks like a flapping wing of a butterfly. That was controlled by cable, and then of course you guys know we don't control it like that anymore, right? Instead, we're going to put a motor right there, and that motor is going to get a signal from the ECM, and the ECM controls it. The ECM looks at a bunch of different inputs, mainly like your pedal. Now has an accelerator pedal position sensor, and roughly that controls this, but that gives the computer the ability to ultimately have control. So if you have that system where it's not non-cable, right, cable-less, would be drive-by-wire. You're using a wire, not a cable. So kind of quite a few reasons for that. They actually can control the throttle better than you can for emissions and stuff like that. And also, if you start to lose traction, and you're like wide open throttle drift mode, it'll be like, no. Close that. And you're like, I got my foot to the floor and it doesn't move. When that system first came out, I can't tell you how many people came in and said, there's something wrong with my GTO. I hit the gas and like it falls on its face and stumbles. I think it needs new spark plugs. And it's sort of like, no. You have traction control kicking in and it's kind of like, blah, 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 blah. That's normal. Well, I don't want it. Then turn it off. Oh, that's it? Yes, that concludes this visit to the dealership. And so, goes past the throttle, goes into the manifold here, which you can see in blue. Now let's define what a manifold is. Generally, a manifold brings multiple chambers into one or one into multiple. So in this case, one throttle body goes to this kind of big like top part that's open. We call it plenum. That's sort of like the gathering area of the air. Then it splits 4 ways and it goes down and it goes into your 4 cylinders. Now on this one, it's a little tough to see, but it's got a fuel rail right in here. So this is a port fuel injection. So all this stuff here is dry. There's no fuel until the fuel injector sprays, and it sprays right at the intake port. What's the intake port? Well, you can kind of see it right here. This is a passage that's built into the head. The intake port is where we ultimately flow into the intake valve, and that goes into the head, which is the top of the combustion chamber. Right, so then from there, if you look at it, I'd say we spin it like this, you can see once it gets into the port, then it's into the cylinder, and you can kind of tell the block has the cylinder in there. So black is engine block, silver is cylinder head. That's kind of the difference. In this one, this is a cast iron block and an aluminum cylinder head. That was like really common for a while. And now, what do you guys think about on newer stuff? You gonna expect to see cast iron block or no? Nah, they're too heavy. They were strong and they were pretty reliable and they made a lot of sense actually, but not when you're trying to improve your MPGs and lower your emissions. So aluminum is gonna be a little bit more standard. I gotta tell you, one of the things that we discuss on here is the head gasket. The head gasket has a pretty tough job. It's got to withstand the combustion pressures. It's got to contain coolant. It's got to contain oil. But additionally, if you think about the iron is going to heat and cool at one rate, and the aluminum is going to heat and cool at a different rate. So they're moving. They're moving separate from each other. So the head gasket's got to be okay with the head maybe sliding across it a little bit and having some movement in there. It's pretty tricky. When they first came out with these, guess what? A lot of head gasket problems. It was just really difficult to have 2 different metals in the engine. The head gasket had to make up for that. So if you think of something from the 90s, late 80s, early 90s, they had some head gasket issues, just the way it was. Right, and then from there, if we go a little bit lower, you get down more into the oil pan, and the oil pan can look a lot of different ways. This one's actually just steel. But on the newer ones, especially aluminum block, you're going to see like an upper oil pan that's aluminum. It's structural. Those are kind of a pain in the butt to change. And then on the bottom, you just got like this little tin metal stamped steel one that's like pretty easy to see all the bolts. Those are a little easier to change. That's pretty typical. And then after we do all of our stuff, we got to breathe it out, right? So the exhaust manifold takes many exhaust ports and brings it down into one. So what's the difference between this and a header? What is a header then? Well, it's just really aftermarket version of a manifold. So this manifold is cast iron. It's kind of beefy. These are reliable. The cast iron is strong. It doesn't crack. It doesn't warp so much. It tends to not crack anyway. A header, if you want a header, you get rid of this big cast iron thing and you make like a thinner, lighter steel tube one, and the tubes would be separate the whole way, right? You pull 4 of them out. To increase your scavenging effect, like we mentioned a little earlier, you could take those headers and you would precision tune the length of the runners. So typically like a longer runner is going to be better for like low end torque. So when it's a manifold, we start grouping the exhaust streams together quickly. With a header, we're going to keep them separate until we get it down to like a collector. So the header is really for performance. Some cars come with kind of like headers from the factory, like that Celica that I had with the 2ZZ, you know, the one I blew up. That one, it was called a manifold, but if you looked at it, it was literally, it was like welded steel. It was a header, but they called it a manifold type of thing. So some vehicles flow better than others. Right here, if the air gets kind of bunched up here and we can free it up, you can gain some power right there. You can gain some power because you can increase your airflow, which means you can have more gas. Kind of make sense? Cool, so that's good overall of the engine parts. We're going to have to go in a lot more detail, so focus right in here. There's basically your systems of the engine. Let's start with the details of the head, and then we'll look at some of these. So here is a cutaway of the cylinder head. As you can see, this is your spark plug. I'd like to start with that one. Spark plug generally is going to be like right in the middle of the valves. That's not necessarily true for all engines, by the way. So if you were to look at this head right here, this is a head off of a 350. It's got a different combustion chamber. The spark plug comes in from the side. So if you were to have it stood up like this, these are a lot heavier than they look, by the way. All right, and I'm going to try to not drop the valves. So I've got one valve pre-popped out for our lecture. The spark plug is actually coming in at this angle. So all the spark plugs are not necessarily in the middle, but pretty much the stuff you're going to work on is going to have the spark plug coming from the top. If you work on an old V8 and it comes from the side, now you kind of know it's just a different wedge-style combustion chamber design. Cool. All right, so from there, let's take a look. We got an intake and an exhaust valve. They look similar. The intake valve tends to be a little bigger. The exhaust valve tends to be made of something different because it's going to get really hot and stuff. But your intake valve opening is going to basically allow your intake port to flow air down into the cylinder. Cool. Then we can close the exhaust valve. We could open up the intake valve. We could open up the exhaust valve and breathe out. Right. So if you look at these, this is the port, goes to the cylinder. This is the port, goes from the cylinder. Kind of make sense? Now let's go in a little more detail. We got an injector right here. So look at where this injector's at. This injector is spraying, and the fuel is kind of like hitting the back of the valve. So what type of fuel injection system would you call that? Port fuel injection, exactly. Now they may have different names. PFI, PG, EMFI, port. They'll name it a million different port ones. They had tune port injection back in the day. But ultimately, the detail was all of those injectors were spraying in the intake port. Now, if you were to go way back, like to this baby right here, this had a carburetor. So I'm going to go ahead and I'm going to show you how you work on the car if it was in the barn. You know, like one of the tuners in my area, his business name is Red Barn Racing. And I just thought that was kind of fun because, like, back in these days, if you want to be a tuner, you could do this in your barn, right? So pull it into the barn, we'll tune it up, you know? We'll get the air cleaner off, take a look at this carburetor, do some little adjustments, tweak some stuff, see how the tailpipe smells. Oh, it's a little rich. Lean it out a little bit, right? You could adjust a lot of stuff on this carburetor because it was made to do that. The negative is there's a lot of little ports and passages and pieces and linkage and springs and stuff. So it's pretty common that it would need a little something. This has no ability to adjust for changes like altitude, these types of things. So this and temperature. So this might need constant little tweaks. Fuel injection is made that you get in the car, you start the car, it looks at everything and it adjusts on the fly using the computer. So it makes a lot of sense. But this was different, right? Air went in the air cleaner, and then right here, fuel was mixed. So air and fuel were going through this intake manifold together already. Make sense? This is not fuel injected at all. This was a carburetor. Now, when we went fuel injected here, this is where we're talking, like where the plenum would be. That would be all dry. And then just at the last second, it would get the fuel. You want to know why? If you mix the fuel in ahead of time, you might get little droplets, you know, that kind of would condensate on the runners. You didn't burn that gas, did you? Did it contribute to your horsepower? No, which means you wasted it, didn't you? And that increases your emissions, lowers your fuel economy, you see. So, like, carburetors were never real efficient. People like them. I don't. I tell you, I'm sorry. I just don't. I got fuel injected stuff. I got carbureted stuff. Fuel injected, if you get it dialed in, it's just, to me, it's just superior. Carbureted stuff, it's easier because you need your pocket screwdriver and that's it. You don't need any laptop, you don't need tuning software, you don't need scan tool, you don't need any of that. But carburetors just tend to always need a little love. So really, carburetors got pushed out for fuel economy and emissions. That was more like, hey, you need to meet these emission standards. Good luck with that piece of crap. Make sense? So you'll see a trend. Generally, we're constantly pushing to get the better fuel economy, to get the better emissions. Now, what do you think is cheaper? Carburetor or 4 injectors and a high pressure fuel pump in the tank?
Carburetor.
Definitely. So some people would go back and be like, oh, cars used to be so cheap it was better. Well, yeah, but they were burning dirtier, they were needing more tune-ups and stuff. So like some people will prefer the past and just be like, I'm just gonna get a carburetor, me and my truck and my shotgun, and we'll be good for life. I don't care if the apocalypse comes. I can adjust my own carburetor. Make sense? You can go somewhere between. Other people like those tuners that run around with the laptop in the passenger seat, constantly tweaking stuff, whatever. It's up to you. All right, cool. So now about this head a little bit though. How do we open, who knows, how do we open the intake valve?
The camshaft.
Oh, the camshaft. And I was sure I had a camshaft, but
There's probably one back there.
I can't find it. Johnny, look for a camshaft and bring it, will you? Be a pal. So the camshaft's gonna have a lobe on it, and the lobe is gonna push the valve open. So like on this one, for example, if you look, you can see it pretty well from here. So we've got a camshaft right here. You can actually see the lobe sticking out. As that camshaft turns, it's going to go around and it's going to basically push on the valve. So I brought a valve over here. I'm pretty sure that I had a cam, but I guess I forgot. So if you look, as that cam comes around, that cam has the ability to push this valve down. When the valve is down, if it's the intake valve, that's when the air flows. But then the valve needs to close, right? Think about this. What makes the valve close? Oh, you guys know a little something already. So the cam pushes down, but then that's a crank. Cam's a little smaller, got a lot of bumps on it. So pushes down, cool. But then the cam has the ramp ends, and then the valve spring pulls the valve back up. That's the whole action. So kind of the difference is if the cam opens it and the valve spring closes it. Closing the valve is a little sketchy, like at high RPMs. It's something I always think of is, you ever heard the term valve float? That's when your cam pushes it open directly, but then you're relying on the spring to pull it closed. So when you're turning that 18,000 RPMs like we talked about earlier, that valve's like, yeah, I'm coming, but like that piston's like, I'm coming right now. Like, I'm gonna catch up to you. And they can, if you're at high enough RPM and your valve is a little sloppy and it kind of floats a little bit, it can actually catch up and smack it. So that would be like true valve float. Technically the valve float is any time the cam pulls away really fast. You got it. Thank you very much. Technically valve float is any time the cam pulls away really fast and the valve is getting pulled up, but the valve is no longer pushing up against the cam. Right? If there's no longer like a direct connection, that valve is kind of floating. It's floating and the spring pulling it back up. Makes sense? A little scary. So I don't like the bikes, but Ducati, for example, actually has a cam to push the valve open and to push the valve closed. There is no valve float. There's no spring. Doesn't need a spring. I don't know about all of them, but I know in at least one of them. So the logic behind that was like, oh, you want to do 16,000 RPMs for the whole race? No problem. You're not going to have valve float. The negative, though, I'll tell you, some of those German and Italian engineers are pretty smart. The negative is this. Now you got double valve adjustment to worry about. So there has to be a precise adjustment between these two. So you can't have them necessarily touching because when the valve gets hot, now it's pushing up against the cam. The cam don't move. It'll actually push the valve open a little bit. And now you have a valve that's not seating all the way. It's kind of trippy, huh? So that's the main purpose of the valve adjustment. Your valve adjustment should have, let's just say, typically maybe like 7 to 11 thousandths, depending, like intake might be a 7 and the exhaust might be 11 thousandths. 7 thousandths of an inch clearance. So it's actually technically not really up against the cam. It's got about 7 thousandths of an inch. Then once the cam rolls and it starts to ramp, then it hits, and then they are touching, right? And it opens all the way, and then it comes back around and starts to close. Once it gets on what we call the base circle, there should be about 7 thousandths clearance right there. Go ahead, Brandon.
What about rollers?
So there's like 10 different types of valve trains, but if it's a roller, the effect is still similar. So like I've got a roller lifter right here. This one is actually out of my Hummer. So as the roller rolls, we still need to have some clearance there. Now I'll give you a sneak preview. What everything I'm saying is like old school. On a newer school, this is a hydraulic lifter. So what we'll actually do, the lifter goes on the top side, and the lifter has a plunger and it's hydraulic. So a push rod lays in there. I'll show you pictures. Push rod lays in there, and then when you set it up, you just get the push rod down a little bit. You'll preload it a bit, and that always keeps just the right amount of tension on it. So as your valve wears, as your valve seat wears, or whatever wears, the cam doesn't usually wear much, but it can. The lifter will automatically adjust it with oil pressure and keep it kind of like pumped up is the best way I can explain it. You know, it's pumped up, it keeps it pretty tight. Whereas before lifters, there was none of that. There was just like a flat tappet roller, or even just flat tappet. It wouldn't even roll, it would slide across the cam. Those would need adjustment. 2JZ, for example, there is no lifter. There's just the cam on a bucket. That needs to be adjusted. Should it change much? Not really. But I'll even give you a little sneak preview. I got a valve here. I'm going to hold it up really close to the camera because I want to point something out. And then I'm going to actually pass this around. This valve is used and it's kind of dirty. So this valve, when you guys get to it, I want you to be able to see this. It's got a little edge that I can catch. There's like an edge right there. You can kind of see it. Yeah, it's a tough one to see. You could tell. I've actually got one that's even worse too. I brought a couple cool show and tell valves. This one's probably worse. So if you look right there, okay, there you go. Yeah, you can tell that valve's got a bunch of wear on it compared to like this valve, which is new. Right? I'm going to pass you two. One valve you're going to notice has like a lip. You can even catch your fingernail on it. That valve, what happened on that valve, this little valve right here is out of one of my dirt bikes. It's a motocross bike. And I've pretty much owned the bike its whole life, but it's a titanium valve. So lightweight, faster RPMs, more power, competition type thing. Titanium is great metal. Wouldn't you say? Doesn't titanium sound cool?
Yeah.
Okay, but it's not that durable though. That's the problem. So yes, amazing for racing. For longevity though, this valve, the valve spring has slammed this valve closed like a bajillion times. And every time it does, it slaps up into the head. And the problem is that titanium's kind of soft, so it wears and wears and wears. Now think about it. Your valve is slapping up into the head, right? So over time, it beats its way further and further up. Remember, you got a cam up here. As the valve gets further in the head, what do you think happens to that 7 thousandths of clearance? 6, 5, 4, 3, right? So the valve clearance adjustment is not generally because your cam is wearing and now it has too much clearance. It's opposite. It's generally because your valve spring has been slamming the valve up into the head and it's recessing. It's called valve seat recession. It's beating its way up into the head and it starts to get tight. Now let's take it a step further. You had 7 thousandths and that's good. By the way, if you somehow ended up with 20, you'd probably hear ticking sound, right? But if you're down under 7, you won't hear anything. You just feel like everything's fine. 6, 5, 4 thousandths, 3 thousandths, 2 thousandths, 1 thousandth. 0 thousandths means it's perfect, but what happens pretty soon, you don't have 0 thousandths, you have -1. -1 means it's actually it doesn't push the cam up, the cam's not gonna move, it's gonna actually be held open. Cool? This valve on my bike was to the point where it's being held open. So I would go to start it and it would be hard to start, it was very hard to get running. It was like, oh man, I need to do another valve adjustment because I I'd go in and I'd see the valve adjustment and get less and less and less, and I'd be like, I don't feel like taking it apart, I'm just gonna run it for a bit longer until the point where it doesn't really want to start. That's a dangerous point, but I said it didn't want to start because it's a 1-cylinder bike. On a car, you won't really feel anything because it's got 3 or 7 more cylinders or something. So you have 1 cylinder with the valve hanging open. Let me explain. This valve gets hot. When it touches the head, it passes its heat off into the head, and the head passes it into coolant and cools it. So if this valve is open, is it ever touching the head? It's never cooling. That's how you burn a valve. You burn a valve, now you got a misfire, now you really need to redo the thing. Make sense? So when we talk valve adjustment, that's maintenance type of stuff. Old engines, we'd have to do those valve adjustments. New engine, we're going to use that hydraulic lifter, and that hydraulic lifter is going to basically compensate the entire life of the vehicle, and we don't really need to worry about it. Except for Honda. Honda still has to do valve adjustments. Talk to Honda, I don't know what the problem is. You can see both. It kind of makes sense? So same concept on the exhaust side. And then this example is a dual overhead cam. So we've got an intake valve, we got an intake cam, and an exhaust cam. And we got a lot of variations. We might have 1 intake valve and 1 exhaust valve. We might have 2 intake valves and 2 exhaust valves. Sometimes we have 3, sometimes we have 5. I've seen them with 3 intake valves and 2 exhaust valves, all kinds of weird stuff. They could have 1 cam for both. They could, like this one cam does intake and exhaust for all 8 cylinders. You know, there's a lot of variations, a lot, all kinds of different ways to do it. So some of that we cover a little bit more later. As far as the head goes, this kind of makes sense. We feel like pretty decent. We'll go into valve train when we cover cylinder heads, which is actually Wednesday. It's that quick, comes up fast. Cool. So we'll continue going down into the block now. So the block is where we got the business end of some things. I'm going to push the heads. This is top end, right? So if I want bottom end, there we go. This is our block right here. Let's say we start with the crankshaft. Now I'm gonna make myself look a little stronger than I am because this is heavier than you think. But this crankshaft right here, and I'm allowed to scratch this is mine. This crankshaft would be down here. As you notice, this crankshaft is like one of the main parts of the engine. The crankshaft is going to spin, so we got the big flex plate or flywheel on the back. When you start it, that flex plate or flywheel gets turned, right? So we're turning the crankshaft. As you turn the crankshaft, that's going to connect to the connecting rod, and that's going to actually move the piston up and down. So this being a connecting rod right here, the crankshaft spins, it's going to up and down, up and down. The piston's going to be on there, up and down. So right from starting, the crankshaft is where we actually apply the motion. Additionally, that flex plate or flywheel is what we attach to the transmission, and that's what makes the transmission turn. And ultimately, the transmission turning turns a differential drive shaft, you know, depending on exactly how it's laid out, even if it's a front wheel drive. All the power starts and ends really at the crankshaft. So the crankshaft's a big important piece. That makes sense? So if we're going ahead and we're pumping, intake comes down, compression goes up, power. Pause for 1 second. All right, so you guys kind of can see the motion, right? Yes. Now to really do this, I got to flip it over. So we're going to pause for that for a second. We got to move this. Yeah, oh my goodness, it's so big and heavy. Why is this so heavy? It's got to be strong, you know that, right? Because we just talked, that has to withstand all those forces. So look at this, but now I'm going to flip it because we're mostly focusing on the crankshaft. Yeah. And that, when we work on that, we work on it upside down, like kind of on it, flip it on its belly, right there. So if you look, I'm going to skip the bolt. Crankshaft's going to live right here. The crankshaft has to ride on what we call the mains, all right? So I'm going to swing this crankshaft back over, and I'm going to point something out to you that's going to be a little tough to show you. So if we look at this crankshaft, you can notice this right here is the center line. This is a main right here. This is not a main. This is a main, not a main, main, not a main, main, not a main, main. The main, it's called the main journals. That's where the crankshaft rides in the block. So if you hear the term main bearings, that's these bearings. The main bearings hold the whole weight of the crankshaft. Kind of makes sense? So this is going to be basically riding on the mains. And as part of the block, we'll actually call those like the saddles. So all those main bearings are in saddles. Do you think they all need to be in line? All centered and stuff? Yeah. Definitely. Now, if we had a problem with one of those, we'd actually pop all this apart. We could lay a straight edge down in there, and we can see our all the mains in line. Now, I mentioned something earlier called line boring. If you had a block and you had a problem with those mains, you could actually send a line bore, which picture, it's not exactly accurate, but picture like a giant drill bit. And the giant drill bit has to line bore all of those together, and that'll get them all in line. Now, the thing is, from the factory they do that, right? But let's just say you're doing all sorts of crazy horsepower and you make a lot of torque on the crankshaft, it could potentially twist the block. If you ever had to line bore it, that's a big deal. Like that's not like, oh yeah, we're just gonna do a quick line bore. Not that many places are gonna do it. Once you do, you're gonna be into it for larger bearings because you can't line bore at the same size. Otherwise you're gonna be missing some, right? So you gotta go bigger. If you have to go bigger, you have to do what's called an oversized bearing. So this is something that people can tend to struggle with. So I'm gonna drop this down for a quick second about oversized bearings. And these, at least I checked one of these is loose, so I'm going to just pick this one. I'm going to pop one of these main bearings out, and then I want to discuss what that oversized means. So this is called the cap, by the way. This is a main cap. This right here is the bearing. So I'm going to just set this down. I'm going to set it down in order so I can put it exactly where it goes. This is the main bearing. If we were to line bore it, you guys know the difference between inside diameter and outside diameter? Outside diameter is like this side of it, right? Inside's like the inside right here. If we were to line bore it bigger, by let's say 10 thousandths of an inch, we'd have to get bearings that are oversized 10 thousandths of an inch. You can see that? They'd have to be bigger on the outside. However, they would need to be the same inside diameter, right? So that's just an oversized bearing. Cool? Kind of get it? Now, if I were to set this down for a moment, and then I were to say, let's just say I could pick on anybody, but I'll pick on myself. There I was stressing out, which is how I lost my hair, because I got so many waders, and there's oil changes, and I drain the oil, and I do the filter, and then I get yelled at by the service advisor. And I'm like, oh, whatever. Okay, the car's done. What did I forget to do?
Oil.
I never put oil in it. Those main bearings are not going to survive very long without oil. The crankshaft is literally supposed to be spinning on a film of oil and never really touch those main bearings. Okay, but I forgot to put oil in there because I'm all crazy, and all of a sudden there's a lot of friction there, right? The crankshaft is spinning because I had that bearing, right? So if you were to take this crankshaft and visualize it, which I can probably get away with this. The main bearing's right here. It has to spin on that main bearing. Cool? But it really needs the oil. If I forget to put oil in there, this doesn't build oil pressure. Now this contacts the main bearing and starts to wear out the main bearing, right? But let's just say it goes even further than that. Let's just say I ship the car. And the customer's like, oh, there's a light on. It's a genie light. I guess I'm going to get my 3 wishes later. And they just drive it. They just keep on driving it. Well, what can happen is there can be so much friction here that the main bearing will seize to the crankshaft, and then guess what the bearing will do?
Spins.
It'll follow it, it'll spin. That's a spun bearing. Think about if I were to have that happen. Not only, yes, it would spin on the saddle, right? And that would be probably having to line bore it, but also, didn't it just wreck the journal on the crankshaft?
Yeah.
So I can get a new crankshaft, and that's probably preferred, but crankshafts are expensive. So I can also grind the journal down on the crankshaft. Now what would have to happen with this bearing to keep that same oil clearance of 2 thousandths? I'd have to get it to be smaller ID. So we could have a bearing that's larger OD, that's oversized. We could have to have a bearing that's a smaller ID because we cut the journal, that's undersized. So is it undersized or an oversized?
Undersized.
It's both. Isn't that crazy? If you cut the crankshaft and you need it to be a smaller ID, that's undersized. But if you line bore and you need it to be a bigger OD, that's oversized. It could be both. Isn't that crazy? If you only line bore it, that's oversized. If you don't line bore it, but you only grind the crankshaft, that would be undersized. But how much? Now this is where we're starting to get into it. Like a rotor, right? We only cut off enough material to fix the defect, correct? Not true with engines. If this bearing is standard and I need to cut that crankshaft, I need to find out what size bearing is available. If they make a bearing that's 10 thousandths undersized, I need to cut it 10. If I only cut it 4, but I put it 10 thousandths undersized, there's not going to be enough oil clearance. Make sense? So it's all about the difference between the two. Now, if you want to understand a little bit better, I'm going to give you a quick sample for math. Math is fun. Here we'll draw our crankshaft, and let's just make it really easy numbers. Let's just make this 2.000. Cool? Exactly 2 inches. Now, if we were to go ahead and we were to cut this down, and let's just say, because it was spun or whatever, and let's just say we took the 0.4 out of it, and then it was clean. And by the way, there's other measurements we need to do. Let's just say we took the 4 thousandths out of it, it was clean. Then we'd look and see, hey, what bearing size is available? And they have a bearing that's undersized, 0.10. This is called 10 thousandths, right? So I really need to not do 4. I actually need to go a little further and take off 10. How would I know when I take 10 thousandths off? Right? Because you don't just set the machine. You're cutting it. You're machining it. How do I know when I've got to the 10 thousandths number?
Can't you measure it?
Yeah, exactly. So if it was 2.000, what should it be when I'm done? 1.990. There we go. 1.990 would be 10 thousandths less than 2.000. Can that make sense? So you're going to see that's a common theme in engine stuff. You don't just machine it till it looks good like a rotor. You got to cut it to a number. And so that way you're going to have the right clearances, etc. Now, similar type of things happen on the rods. So remember we talked about mains? Well, let's talk about rod journals now. So again, I was showing you, this is a main. This one kind of looks like a main, right? Because from your perspective, but by the time I turn this crankshaft, is this sucker in the center line? No. So actually what happens on that one, we're going to connect a rod to that. So that's a rod journal. Make sense? So that's actually going to get a rod, and then the rod is going to take a piston, and that's going to go up and down the cylinder. Those have bearings too. What do you think those bearings are called? Yeah, connecting rod bearing or a rod bearing. By the way, the connecting rod bearings, those have a harder job than the mains. That connecting rod bearing has to take all the force of that whole one cylinder and rod, right? So if that cylinder gets a combustion stroke, that connecting rod is being rammed right into this journal, just that journal and just that bearing. See how the mains kind of all work together? The connecting rods don't really. The connecting rods work solo. So when the combustion's strong, the rods get kind of beat up. Go
I was
ahead.
gonna say, so you would argue that if, like, let's say there's a loss pressure when it comes to oil,
Yeah.
the connecting rod bearings will fail first.
Most
then the
likely.
bearing?
Yeah,
I
most likely. And Andres, I forgot you raised your hand. I ignored you. I didn't try to.
had an argument about.
It's about balance.
Okay, how about Wednesday? Okay. So you guys kind of understand the difference between mains and rods? Now let me just give you like a quick explanation. If you had an engine and it was knocking, it can be a little tough to tell sometimes if it's rods or mains. Mains tend to be a little more consistent, thumpy. Rods tend to be a little more clattery, but the thing to do, let's say this was cylinder number 1. If cylinder number 1 rod bearing has an issue, when you make a power stroke, you're going to get this, right? Because it's hitting, and let's say it's worn out, it's loose. What if you disabled cylinder number 1? You pulled the spark plug wire, you disconnected the injector. What would happen?
Misfire.
it would misfire, but what if the noise went away or severely decreased? That would kind of tell you it's number one rod bearing. Make sense? So remember, the noise from a rod bearing is mostly the result of the combustion slamming it into the crankshaft. You take away the combustion, you take away the slamming. So we've had an engine, for example, it's actually a T10 student. Everybody's had dumb moments, okay? So he had a Crown Victoria, and it didn't, well, let's just say he asked us to look at it while he was in electrical and we were in engines. He said, it has a knock, can you diagnose it? I said, yeah, we'll diagnose it. We heard it, it was, you rev it up. Ooh, that sounds like a rod bearing. We could tell the customer right there, well, you got a bad rod bearing, well, what do? You need a new engine. They're going to be like, are you sure? That kind of sucks, that's it? You just listen to it and you tell me I need a $6,000 job? So we took it a step further. And what we did, we disconnect cylinder by cylinder. Cylinder 1, grrr. Cylinder 2, grrr. Cylinder 3, silent. Cylinder 4, grrr. It came back, right? So in cylinder 3, we disconnected it, the noise really went away. So we went back to him saying, perform diagnosis, check this, and this, found you have a bad number 3 rod bearing. Most likely other rod bearings will be damaged as well. You really need an engine. Wow, great job. You did all that in that amount of time? What did we do? Freaking disconnected injectors for like 2 minutes? Because we knew what we were doing and we were really able to nail it down to, hey, it's not only do we know it's a rod, we know it's that cylinder right there. You could, if you really know what you're doing, you could do a lot of quick diagnosis. Makes sense? You can make sense of that concern very quickly. Right? So now, this was the number 1, but actually it also shares 1, 2. Yeah, 1 and 2 are actually on this journal right here. On a 4-cylinder, typically it's 1 and 2 and 3 and 4. But on a V8, because they bring the 2 cylinders together, cylinder 1's in the front and 2's in the front on the other side. They both actually share this journal. So this is a combined journal right here. Now you're going to see we would need to do some more measurement to really check this crankshaft out. But I think you guys get the idea for now, because I got some better pictures later. Cool. And then additionally, yes, we have the connecting rod. So remember we were talking about undersized, oversized? If we were to mess up that journal on the crankshaft and we had to cut it down, that would be undersized connecting rod bearing. But what if the bearing were to spin on the connecting rod and get it all worn out? We could either A, get a new connecting rod, which would make sense. But if it's like this one's a nice I-beam, this is a nice connecting rod, it's expensive. You could actually oversize this connecting rod, resize the big end of the rod, and you could get an oversized bearing. So if we were to resize this 10 thousandths, you could get a 10 thousandths oversized bearing, while also potentially having it be undersized if you cut the crank too. See how that's kind of crazy? And then here on the top we have a piston pin. So this one, this is a piston. You can see this one's got some miles on it. This one's mine. So this piston pin, also called a wrist pin, is partially pressed out, and that's actually one of the retainers. So I kind of held on to that. You can have issues with the piston pin too. That's possible. Sometimes they'll call it a wrist pin. Why do you think? Yeah, I mean, pretty much your piston looks like that anyway. That's what it's doing. So wrist pin, piston pin, similar. More about the piston. This one is high performance. It's got valve reliefs. That means this is probably fairly high compression. Anytime we're going to run this piston up further, closer to the valves, we could be concerned about the valves hitting, so they did valve reliefs. It's pretty nice. Not all of them have that. This one, for example, this is a different type of piston, but it's got a coating on here, like an anti-scuff coating. So different types. And then, let's say we look at cylinders. That's the next thing we need to discuss. When we're talking about engine rebuilding, a lot of our concern is right there in the bottom end with those mains and rod bearings. That's very common. But also, we got some concerns about cylinders. So here you can see we've got a V8. Now, are these cylinders good or bad? Does this need to be machined? Can it be honed? Does it need to be actually bored over? You tell me. I don't know. How do you know? Yeah, you can look like this, but look doesn't tell you everything. Because look, is this cylinder round or out of round? It looks round to me. If I were to draw another circle, okay, you ready? Here we go. Round or out of round? Okay, that's out of round by a lot. That looks like it's round, but if you really want to know, you'd have to actually measure it, right? So if you want to know if it's out of round, how would you know?
Measure it.
How though? How? Yeah, just like a drum. Exactly like a drum. You have to measure this way and this way. And they should be the same, but as you can see, this one's longer, huh? We've got a little bulge right here.
Use the tool that has like those two little rods, right?
You can use the telescoping gauges, but we're going to cover all how to measure it when we actually measure them. For now, I just want you to know concepts. So that cylinder could be out of round. If that cylinder is out of round, it's not going to have great compression. It's probably going to have oil consumption and stuff. So people will be like, oh yeah, I rebuilt my motor in my garage. Well, I was wearing Crocs. Where are them Crocs at? There, the purple Crocs right there. All right. You can't, there's some people who are pretty smart. I mean, they rebuilt some stuff. But I had a guy come in and he said, oh yeah, I bought this car. I could make this about several different students. I'm just going to pick one. So I bought this car, whatever, and the guy rebuilt the engine and everything's all good, but it burns oil. Well, they might have rebuilt the engine, but if it's burning oil really probably is coming from inside the engine because that's where it lives. So something's wrong there. Now, one of the cars was turbo. Possibility it could be turbo seals, these types of things. There's a possibility it could be a problem with the PCV system, but there's also a possibility that it had an out-around cylinder and they just put new rings in there. New rings don't seal out-around cylinder. So how out-around can you get? Typically anything 1,000th or more that's it, you're done. You can't see that. You have to measure that. If you don't measure that, you're just guessing. You might as well be rebuilding the engine in your garage with your purple Crocs. Make sense? Not to say there's anything wrong with that, but like to really do it right, you need to have all the equipment. It's probably not going to happen in the garage over some adult beverages while football games going in the background and